Hello, this is a lecture for industrial robotics. So today I'm going to talk about a little bit of background about robotics and also different robotic control systems and so we can recognize how these robotics works and what they are, and I'm also going to discuss a little bit about what some of the end factors, how those what kind of application those robotic can work, and what kind of tools or devices, and also the grippers you're going to use for for actions. And lastly, a little bit of application about industrial robots and how they are used in the industry. First, the reason that we need to use industrial robotics is because some of the working environment can be a little bit hazardous to for human being. So then we can use some of the machines to help us to do those operations. And also human always makes errors, mistakes, and also their operations are not consistent. So by robots, they can make consistency and also accurate operations that is programmed and also defined by the humans. So that's compared to human operators, robots have that advantage. And also robot can be reprogrammed. So if you want to revise the operation, we can always reprogram the robot to do another operation. So he has a lot of flexibility. And the robot, what is the robot composed of? So robot is composed of actually manipulator. It basically that consists of joints and links. So joints are these, right? So they provide some of the relative motion, while the links are those rigid components between the joints. These are the links, and the typical joint types, they are either linear or rotary joints, and how much you can move is called degree of freedom. Sometimes we can move backward, forward, left and right, up and down, or all these are rotating. So these are the degree of freedom. Now let's look at one video. It talks about 6 degrees of freedom of the robot. Where these 6 degrees are. All right, so that's how the 6 degrees, where those 6 degrees of freedoms are. And typically, a robot manipulator is composed of 2 sections. One is this body and arm. So body and arm is just the whole whole component, and another part is wrist assembly. So basically for orienting of the objects. And there are different types of joints in the robots. So when you go out and look at all these different robots, actually you can see many different shapes, looks. And sometimes it does not have to look like human arm or human being or animal. It can be any kind of shape that may be designed only for a specific operation. So that's why people have designed many different types of the joints. The one is the linear joint. So basically it moves as one axis. So it's more like push and pull motion. And another one, orthogonal joint, which is a B here. You can see when the joint motion is moving left and right, it triggers another motion, which is the output link from here, right? So it forms a 90 degrees of the angle here. And also there are a lot of rotary motions. For example, this type R, which is rotary inertial motion. We have seen that in the prior video. Also, there are some of the joints are like twisting joint. So twisting joint is where you can twist the two links. So this is the twist link. So basically this is how it works. Another one is a revolving joint. So revolving joint means this input link can rotate or spin, right? It will trigger the output link to move as the kind of a circular direction. So these are the different joints and also the motions. And there are based on the application and also the function of the robots, there are many different body arm configurations. Typically there are 5 common ones. We're going to look at each one of those. And the first one is it's an articulated robot. We have seen that in the prior video. Now let's take a look at it again.
Industrial robots have various axis configurations. However, the vast majority of articulated robots feature 6 axes, also called 6 degrees of freedom. 6-axis robots allow for greater flexibility and can perform a wider variety of applications than robots with fewer axes. Axis 1. This axis, located at the robot base, allows the robot to rotate from left to right. This sweeping motion extends the work area to include the area to either side and behind the arm. This axis allows the robot to spin up to a full 180-degree range from the center point. Axis 2. This axis allows the lower arm of the robot to extend forward and backward. It is the axis powering the movement of the entire lower arm. Axis 3. The axis extends the robot's vertical reach. It allows the upper arm to raise and lower. On some articulated models, it allows the upper arm to reach behind the body, further expanding the work envelope. This axis gives the upper arm the better part accessibility. Axis Axis 4. Working in conjunction with the axis 5, this axis aids in the positioning of the end effector and manipulation of the part. Known as the wrist roll, it rotates the upper arm in a circular motion, moving parts between horizontal to vertical orientations. Axis 5. This axis allows the wrist of the robot arm to tilt up and down. This axis is responsible for the pitch and yaw motion. The pitch or bend motion is up and down, much like opening and closing a box lid. Yaw moves left and right like a door on hinges. Axis 6. This is the wrist of the robot arm. It is responsible for a twisting motion, allowing it to rotate freely in a circular motion, both to position end effectors and to manipulate parts. It is usually capable of more than a 360-degree rotation in either a clockwise or counterclockwise direction. The most popular 6-axis robots are manufactured by Motoman, Fanuc,
Alright, so this is the articulated robot configuration. Now, another one is the polar configuration. You can see the polar configuration is composed of the bottom as the rotation axis or rotation freedom, the degree of freedom, and then you're gonna also have a linear, at one end of the configuration. There are not a lot of videos for this polar configuration. There is one. It's close, a little bit close. So you can see how it works, with this setup. But this picture is actually it's a better description of the configuration. Another one is Scara robot. So this is also a common one we used, and because these ones are usually that it's a fixed arm, but also it can be make it flexible. So it looks like more of a shoulder and elbow joints. Alright, stop here. If you want to watch it a bit longer, you can just click that link in the slides. And another one is the coordinate robot. So it's more like our traditional how to say, it's control system with XYZ axes. For example, in CNC machines we have this. In 3D printing we also have this. In a lot of machines, as long as there are 3D axes, it's a similar setup. All right, so this is a Cartesian coordinate robot. Another one is a delta robot. So delta robot is it's made of 3 arms. So and they are attached to an overhead base, and each arm consists of 2 rotational joints, and you can see it from the figure. And all the 3 3 arms that connect to a small platform at the bottom. So this is the platform at the bottom here. So the N factor can be attached here either to pick up something or move something.
Now, his thing, the hexapod.
Okay.
I think there's discussing it with him on Sunday, I think there's a fundamental, I'd like to say software because I'm not a software guy. What'd she say?
Don't take his word for anything.
Thanks, Ruth. Well, it's a good thing I'm recording our sound here. He's using,
What did you say about her?
Ruth.
All right, ignore that conversation. Just focus on the robot. And so after we talk about the body and arm configuration, now let's look at the wrist configuration, which is at the end. Where we have a lot of moves. Usually, wrist configuration have tool at 3 degrees of freedom. For different kind of operations, and it's attached to the end of the arm, and also N effector is attached to the wrist assembly. So the N effector means the actual tool that is used for the operation. Either say if you want a pen, okay, that is pen. If you want a machine, like a machine. If you want to do spray, they can also spray. So many different options can be attached to that to the wrist. And so in terms of degree of freedom, typically there are roll, pitch, and yaw. We watched a little bit about that. Now let's look at a bit more details about the 3.
Robots come in all different shapes and sizes, but are frequently classed by their degrees of freedom. Each direction of movement on the robot is considered an axis of movement. This robot rotates at the waist, bends forward and back at the shoulder, and moves vertically at the elbow. Each single movement axis is equal to 1 degree of freedom. This particular robot is equal to 6 degrees of freedom. It moves along 1 axis for each of the waist, shoulder, and elbow joints, and along 3 axes at the wrist using pitch, roll, and yaw. These particular motions help to locate the tool in the work area and are called position axes. Most robots have at least 3 position axes to help position the tool in the work area. If the robot were to slide along a track, it would have a 4th position axis of linear movement and another degree of freedom. While the position axes locate the tool in the work area, the orientation axes help orient the tool in relation to the workpiece. The types of movement along orientation axes are defined as pitch, roll, and yaw. These movements all occur from the same joint, the wrist, but along 3 distinct axes. This type of movement is most easily illustrated as it relates to aircraft movement. The robot's tool moves in the same way. Pitch moves the tool vertically. Roll rotates the tool about its center axis. Yaw turns the tool left and right. The position axes movement at the waist, shoulder, and elbow, along with the orientation axes movement of pitch, roll, and yaw, allow the robot to accomplish its tasks within the work envelope.
Alright, so in the video we talked about the work envelope. So what is work envelope? It is also called work volume. So basically it's a 3D space that is, the robot can manipulate at the end of its wrist. Basically this is the workspace, right? How much it extend, how long it extend, where it can, perform its operations. And so you probably can tell, the work volume or the work envelope is actually determined by how many types of joints and what is the range and also size of those joints and links. And so you can see from these are a typical table for those common configurations. For example, articulated a robot, the work volume is more partial sphere work volume, and the polar and be also the partial sphere. While the Scara, like picking ones, it's more like the cylindrical, because it's more picking, right? And the Carson coordinate is rectangular, solid. It's a coordinate, system. And then the delta one also it's a hemisphere one. And in terms of the drive, joint drive systems, it can be from different powers. One is electric powers. Electric power means they are using electric motors, right? Motors to actuate those actions. All right, so this is the electric. Another one is hydraulic ones. So hydraulic one use actuators, the pistons, right, and also some other rotary, actuators. And because they're using hydraulics, so that's why it's commonly used in the very the task requires really high power and lifting capacity. And another one is a pneumatic. So pneumatic compressed air. As we know that compressor air, the power of compressor air is actually a little bit low. So that's why those pneumatic actuators or robots drive systems can only be used in some smaller robots and some simple or small or some tasks that does not require a lot of power.
Since retirement, I've been trying new things. With Frank's Red Hot, I put that on everything.
you can see a lot of these setups and actuators are actually similar to the PLC ones, that is triggered by the pneumatic compressors. And the sensors that are typically used in robotics, there are internal sensors and also external sensors. Internal sensors are used to control the position and also velocity of the manipulator joints. So basically to move, how fast and where to move all those joints and the links. Well, the external sensors basically to provide feedback that how this robot can interact with external environment, right? So typically ones those tactile sensors, proximity sensors, machine vision, or some other temperature environment sensors. Now let's look at the tactile sensors.
Hi, I'm Joe Romano, a PhD student at the University of Pennsylvania and a summer intern here at Willow Garage. My work this summer focused on having the PR2 understand tactile information. Using tactile information, we were able to make the robot delicately grasp and manipulate objects, place objects down, and detect contacts between the robot arm and the environment. Previously, without tactile feedback, the strong robot joints would crush many household objects and be unaware of unexpected contact events. Using sensors in the hand of the robot, we're able to do delicate and responsive control of the PR2 gripper. The robot is able to close its hand around objects in the world, recognize the moment of contact, and stop quickly before damaging the object. During manipulation, the robot detects objects slip and increases the grip force to stabilize the grasp. When placing objects down, the robot detects contacts with the table through its tactile sensors and gently stops its motion and releases the object. We have found that tactile information is also a useful goal in handing objects to a human. When the robot has decided to hand over an object, it is able to detect when the object is being pulled from its grasp, a natural signal to release the object. Tactile information has also been integrated into the robot's motion planning algorithms, and it's now capable of recognizing when it has made unexpected contact with the environment, stopping to avoid further damage to both the contacted object and the robot itself. The PR2 is now capable of detecting and responding to tactile events in a fast and natural manner. This work was done at Willow Garage with the help of Günter Niemeyer, Kaijin Shao, and Sachin Chitta. Further code and documentation is available at ross.org.
All right, so also some touch sensors. So this is the difference between tactile sensor and without tactile sensor. Another sensor is a proximity sensor, so you can observe where the object is, and then provide some of the feedback to the control and adjust the motions. All right, so that's and also another type of sensor is optical sensor. So you can, for example, machine vision by scanning the whole whole picture of the system, and you can identify where the part is, and then start to adjust the control.
Markets change fast.
So from this setup, you can tell, the parts that actually have different laying on a different positions. Some are, have the bottom on the app. Sometimes have the other side on the app. So and then the machine vision will have to identify where the part is actually fits for that position, and then pick up the right one to for the operation. Also, some other sensors we like, environment sensors like temperature or the voltages or energy. And type of controls, and some of our very simple robots will be limited sequence control. So basically, you tell the machine what to do, and then it will keep doing that, and it's very simple. Some of the robot, some of the controls can play back, so which means you can record the work cycle. If you program it, and then it just record the prior work cycle and then repeat it again and again. And the work cycle can be either the point-to-point control, or point-to-point pass, or it's continuous pass. Some other robots, is especially in recent times, that the robots have more intelligence, which means that they can react to the environment and then to make its own decisions or communicate with humans on some operations. So this is more intelligent controls. And any factors. So any factor, basically those are the tools for for the robot to perform different operations. And two typical types. One is the grippers, the other one is tools. Grippers are those having those grasp, right, move operations. Well, the tools will be for different manufacturing processes. Let's first look at this overall gripper video. Gripper can be designed in this way, to pick up a pallet. So sometimes they can, suck the sheet, either a metal sheet or a piece of sheet, and then place to another place, or you can grasp. Depends on what kind of manufacturer you want to put there. All right. Different gripper types. Now, first, let's look at this mechanical gripper. This is how the mechanical gripper works. It's connected to a motor, of course. It's all made of mechanical joints. Another one is vacuum gripper. So you can use vacuum to get the material. Also, there are magnetized grippers. So they use the magnetic gripper to get the metal pieces. So this is how magnetic grippers use. And also there are some adhesive devices. And while recent advances in the mechanical grippers that some of the grippers that not only have one gripper at the end effector, does not have only one gripper but also have multiple grippers or multiple fingers. So here you can tell they have two grippers. And also multiple finger grippers. And others will be like you can also implement some of the interchangeable fingers. For example, if you want to work on another operation and then you figure out, okay, the original finger is not working well, then you can just change to another type of finger so it fits better for the new operation. So having this interchangeable will make a lot of flexibility for the robot. Also, the sensor feedback technologies, you can sense the presence of the object and then to react, right? It's uh, it's good to have standardized gripper products because in designing of the robot, usually that requires a lot of technological effort, and it's also a time-consuming effort. And if we can keep a lot of things standardized, it will we will save the time and also can produce more more products, robotic products. For some of minor customizations, it does not need that much of the customization. In fact, so that's why standard scrapers are always desired. Some of the applications of industrial robots, we can look at some videos on how they are used in these applications. First, material handling. These are material handling, and also machine loading and unloading, especially when I use the CNC machine. Loading a part on the CNC machine. It's a turning machine. So after the operation, I also unload the part. And spell welding. Spell welding has been used a lot in the vehicle, making companies. Also spray coating. Some robots can be used in assembly as well.
Clear Automation developed this fully automated mounted FANUC LRMate 200ID robots, a FANUC M10IA robot, as well as custom winding, wire handling, and connecting mechanisms that produce 6 different harnesses ranging from 20 to 200 feet in length. It produces 6 electrical harness assemblies. The ID robot picks new wire from the decoiler, clamps it into place in a winding head, and the machine winds the wire to the appropriate length as selected by the operator through the HMI. Once the appropriate length is coiled, the wire cutters snip the wire, and the LRMate handles the end of the wire back into a clamp within the winding head so that the coil doesn't unravel. One LRMate is responsible for 2 turntables that include 6 coil winding heads.
So this is how it's used in the assembly. It can also perform some inspection operations, for example, engine block inspection, looking at the dimensions and some other characters. Some of the robots can actually work with humans, so we call it collaborative robot to perform a task together with a human being.
For more than 85 years, Omron has helped perfect the art of building machines, working together in perfect harmony. A robot so versatile, it adapts to any number of tasks. Guided by a state-of-the-art robot vision system designed to recognize a reference point, the robot can be moved and perform its tasks with no additional setup. Also collaborates with other machines, performing a wide range of applications relevant to almost any industrial environment. From machine tending to pick and place to screw driving.
All right, so the reason sometimes we have to do this collaborative operation is because humans have some advantages, like it's more intelligent, and also it has higher adaptability and also problem solving abilities. Well, these are machines just do not have. And as we mentioned at the beginning, and now we can see in those applications, those industrial robots are typically used in the environment that have some safety concerns or hazardous working environments, or some of the simple jobs that require a lot of repetitive work cycles, are difficult to handle by humans. All these all these applications, it's better to use an industrial robot instead of a human being. With more automation and also robotic arms or robotic actuators implemented in manufacturing and also in our lives. Actually, there are recently a lot of discussions on the job loss. Because of the technology development in manufacturing, but this is a technology evolution, and when some of the jobs, especially in the manufacturing, will be replaced by some higher technical positions. For example, if you are implementing those robots, then there will need a lot of engineers, right? Engineers need to think about how to program those, how to maintain, how to manage all these programs. So it's just different type of the positions. This is how the human civilization evolves. There are some of the jobs that will be gone, because of the higher technical content, but there are a lot of new positions, new jobs will show up because of new technology. So this something about robot discussions about future jobs related in manufacturing. All right, so that's all for today. Actually, I also want to show you another video that about robots. Maybe you can search here. So there's a very famous company. It's called Boston Dynamics, and it developed a lot of videos. We can probably. I think this video. There's an evolution about Boston Dynamics, and you can watch what are the recent advantages in or advances in robot development.
Style uninterrupted.
All right, so that's all for today.